Okay, so what we're going to do is go over the relationships quiz I gave you on Schoology last week. So before I get started looking at the specific questions, I'm just going to take you through a few key points about the three types of relationships that we met. So let's start off with that. So far in physics, we've met three kinds of relationships. Met directly proportional as part of year 7. Linear, again, we kind of looked at in year 7. Inversely proportional, we met for the first time this year. So let's break down the key things we're looking for to spot these relationships when we collect data in an experiment. So firstly, a directly proportional. If we have plotted a graph, so here we've got a very generic graph where we've got our independent variable and our dependent variable. If the graph is a straight line, that's the line of best fit is straight, and it goes through the origin or goes through 0, 0, that tells us we've got a directly proportional graph. Okay, so that's how we spot it from a graph. If we just have a table of data that we've collected, so again, we've got our independent variable and our dependent variable. If we calculate I over D, so independent divided by dependent, so here to get the 1.8, I've done 2.0 divided by 1.1, and I've done the same thing here, so 1.4 divided by 0.8 gives you 1.7, blah, blah, blah. So if your ratio is constant, so when we say constant, we mean constant within experimental uncertainty, we are seeing a directly proportional relationship. Now, as it says here, we could have done dependent divided by independent and shown that's constant. That is fine. So let's just add in that one little bit, actually. So the value doesn't have to be exactly constant. The values... Okay, so they just have to be within experimental uncertainty. So when we're doing experiments, the values that we measure are never exact. There's always, so this 2.0 in the table, it could realistically be 2.1. It could be as low as 1.9. We've got some uncertainty about that value. So we're not expecting to get exactly the same values here, but we're expecting them to be close to one another. So they are within experimental uncertainty. Okay, so that's directly proportional. We'll also take a look next at inversely proportional, which we've met more recently. So again, same type of graph. We've got the independent variable, dependent variable, and this time we've got a graph that looks like this. So what's different about inversely proportional is we can't spot one just by looking at a graph, but the graph can give us a clue to actually check for one. So for example, if I saw a graph like this, I wouldn't bother checking for an inversely proportional graph. Okay, I would see this and go, oh, this is directly proportional. I don't need to worry about inversely proportional, because you can't be both. You're only ever one of these things. So with inversely proportional, if I see a graph like this, I'm like, aha, I should check for an inversely proportional graph relationship if I'm seeing this. So what I'm looking for that's telling me that is I'm looking for a negative decreasing gradient. So a negative gradient is any line which is sloping downwards. Okay, so this is just an example. So we could have, just so I'll delete it in a second, but a negative gradient could look like this. It could look like this. So there's lots of ways of having a negative gradient. Okay, but this one and this one would not be indicators of a inversely proportional relationship. So let's get rid of those. What we're looking for is what we call a decreasing gradient. So you can see the line, the steepness of it, which is what gradient really means, is getting smaller over time. So it's really steep here, but the steepness is decreasing. So that's what we mean when we say decreasing gradient. The steepness is decreasing. So if I'm seeing a negative gradient, it's also decreasing. That tells me I should check for an inversely proportional. But in terms of how you actually check for it, what we need to do is multiply the independent and dependent variable values. So you can see to get 0.9, that's 2.0 times 0.45. And we've done that for every line in our table. And again, this time it's the product. So the multiplying of the two is a constant. That tells us it's inversely proportional. And that's the only way of checking for an inversely proportional relationship. You have to look for this here. And again, they don't have to be exactly the same. They just have to be... So the can't spell today. Constant value but so it must be within experimental uncertainty again. So this is idea of experimental uncertainty is something that crops up quite a bit. Okay, so we got 0.9, 0.7, 0.8. I'm happy that that's pretty much constant within the uncertainties of our experiment. So the final one I want to take a look at is something, again, we can spot from graphs, but we're not really going to spot in tables. So it's kind of the opposite of inversely proportional. So anytime you have a graph where the line of best fit is it's a straight line or a constant gradient, we could also say, that is indicating we've got a linear relationship. So it doesn't matter if we have a positive gradient, a zero gradient, or a negative gradient. If it's a straight line, it's what we call a linear relationship. So something to look out for in terms of spotting them is, remember, we don't have to start graphs at 0, 0. So this graph you can see is started at 10, 20. So what I'm looking at here is a linear type relationship because we can't actually see whether it goes through the origin or not by looking at this graph, but it's definitely a straight line. So it is linear. So the thing I'll write here at the bottom. So directly proportional is a specific type of linear relationship. So think of it, so direct proportion is like a subcategory of linear. So any straight line graph is a linear graph. If it happens to go through the origin, we don't call it linear anymore, we call it directly proportional. But what that means is that direct proportional is just a specific type of linear relationship. Okay, so now let's go back to the quiz so we can review what I was actually looking for in these answers. So, looking at our graph, what relationship is shown? So the things I'm looking at, so straight line graph, so it's definitely a linear type, but it goes through 0, 0 or through the origin, which means it's directly proportional. So we're more specific. It's not just linear, it's directly proportional. So that was our reasoning here. So there are two things that I was looking for in terms of the reasoning. So the line of best fit and again, the line of best fit is straight and it passes through the origin. So it doesn't have to go exactly through the origin. Again, we're going to see this phrase again. So within experimental uncertainty. So if it goes slightly above the origin, slightly to the right, slightly to the left, slightly below, as long as it's really close, we'd still say it's a directly proportional relationship. Okay, so looking at this next one. So we've got, again, straight line, so definitely linear. But you can see our origin down here is 0, 0, so it doesn't go through the origin. So it is just linear, it's not directly proportional. So the things I'm looking for here, so the line of best fit is straight, but the line of best fit does not pass through the origin. Okay, so then what relationship is shown by this graph? So looking at it, it could be inversely proportional because we've got a negative decreasing gradient, but we don't have enough information. We would need to know values on this graph before we can actually check it's inversely proportional there. So looks like it could be inversely proportional, but we don't know. So we haven't got enough information. So things I was looking for here. So it's definitely not linear, directly proportional. And the reason for that is the line of best fit is not straight. And so it could be inversely proportional. And the reason for that is the gradient is negative and decreasing, but there is not enough information. We need to check that the independent divided times by the dependent is a constant. So that's the information we need there. Okay, so next graph. So what relationship is shown by this graph? So it's a straight line graph, so it's definitely linear. We don't know if it goes through the origin or not, because you can see we started our graph at 2010. So it's definitely linear, but I suppose it could be direct proportional, but we don't have enough information to say that or not. So the line best fit is straight. So it is. So we don't. So we don't have enough information to say if it is directly proportional or not, because we don't know if it goes through zero or not, but it's definitely linear. Okay, so that's graphs. We'll actually now have a look at some data as well. So what kind of relationship does this table show? So first of all, I'm going to look for clues. So you can see here, the independent variable is roughly doubling, and the dependent is also roughly doubling as well. So that's telling me to check for a directly proportional relationship. So that's why I'm deciding to do that check. What we're going to do is I'm going to do the dependent divided by the independent. So 1.6 divided by 1. I'm going to do 3.51 divided by 2.2, 2.58 divided by 1.6, and 5.57 divided by 3.5. And when I do that, I get pretty much the same value every time. So let's actually see those calculations. So you can see I did d over I. I could have done I over d. It doesn't matter. But every single time I got exactly 1.6. So there is a directly proportional relationship. Okay, so that's how I got this answer here. So let's move on to the next one. So the reasoning here. So theta it. So the first thing I saw that is when I doubles, D roughly doubled as well. So that was my clue that I was looking for. But in terms of how I actually checked, so in the experiment, D over I. So D over I gives a constant value within experimental uncertainty, so it is directly proportional. So that is our actual evidence that it is directly proportional. So this is our clue that tells us to then do this next step here. If we didn't see something like this, I wouldn't bother checking for this one here. Okay, so let's move on to the next one. So again, looking through here, so when the I value doubles, so goes from 1 to 2.2, the dependent roughly halves. So that's telling me I'm going to check for an inversely proportional relationship, because whereas I gets bigger, D gets smaller, so it's definitely not a directly proportional relationship. So let's check. Okay, so let's go to my actual data here. So I've done I times by D for all of the values. And so looking at this, our I times D value is changing quite a lot. So I would say I and D are not inversely proportional, as the product is not constant. And then I and D are not inversely proportional, not inverse, are not directly proportional. Let's get that right. are not direct because as I increases, D decreases. So we would be looking for I and D both going up there. Or we could have also said that I over D is not a constant value. And that's actually probably a better way of checking. So if you do I over D for all of these values, we don't get the same thing. So that would probably be a more conclusive way of saying that. So this one here, neither directly or inversely proportional. So I times by D is not a constant value. I divided by D is not a constant value, even within experimental uncertainty. So as we learn more about physics, we actually learn what significant experimental uncertainty looks like, but we're not going to worry about that much for now. So let's have a look at one final one. So what kind of relationship do we have here? So things I'm looking for. So when independent doubles, dependent again, what's happening to that? That's about 1.2 to about 0. Yeah, so return is roughly halving. So I'm going to check for an inversely proportional. This isn't going to be a directly proportional relationship here. So let's double check that. Okay, so if we jump onto where I've done the calculations, so I was checking for inversely proportional, so I've done I times by D, and you can see that comes out as 1.2 for all of these different values, so that's showing an inversely proportional relationship there. So let's go back. So we've got an inversely proportional relationship. So the first thing I said is when I doubles, D roughly halves. So this isn't any evidence, but it's my clue to check for it. So product of I and D is constant within experimental. So that's how I actually checked it. Is the product of I and D being constant? That's what told me it's inversely proportional.